In this presentation, we tackle one of the most operationally decisive problems in a container terminal: how to assign quay cranes to vessels that are already berthed. The assignment determines how fast each vessel is worked, which directly affects vessel turnaround time, terminal productivity, and whether contractual departure windows are met. The challenge is that crane assignment is not just give more cranes to the biggest ship. Every vessel has minimum and maximum crane limits. Crane productivity can vary, and cranes working too close together interfere and reduce effective throughput. The goal is to assign quay cranes to vessels to minimize total service time. In operations terms, you want to clear the vessel workloads as quickly as possible while using the crane fleet efficiently. The constraints are what make it a real problem. Each vessel has minimum and maximum crane requirements. Each crane can be assigned to at most one vessel at a time, and interference means adding a crane can sometimes reduce marginal benefit if it crowds the work area. Picture the port of Rotterdam at 6 a.m. on a typical Monday morning. 7 large vessels are berthed along a 1,200-meter quay, and the terminal has 12 quay cranes available. The workloads are substantial and different across vessels. One vessel has 2,400 containers to discharge, another is waiting to load 1,800 containers, and another requires 3,200 total container moves across discharge and loading. The operations manager must distribute cranes across these ships quickly because the next decisions will set the day's operational rhythm. A crane allocation decision is not local. It affects vessel turnaround, berth congestion, and downstream yard flow. When a high workload vessel is underserved, it creates long completion tails that block berth capacity and amplify congestion. There are also productivity traps. Over-concentrating cranes on a vessel can trigger interference and wasted capacity. And if you ignore uncertainty such as slowdowns, breakdowns, or weather effects, a plan that looks good on paper can collapse in execution. Assignments must balance productivity and feasibility. Each vessel has contract-driven minimum and maximum crane limits, so you cannot freely allocate any number of cranes. Meanwhile, cranes assigned too close together interfere and reduce effective productivity. Uncertainty increases the difficulty. Real operations face variability in processing time, equipment condition, and disruptions. The choice you make now determines whether vessels depart on schedule or face costly delays that ripple through the network. We use a tiered solution approach. Tier 1 is a stochastic programming baseline that models uncertainty using scenarios and optimizes expected performance. Tier 2 uses beam search, a heuristic that explores multiple promising partial assignments without exploding compute time. Tier 3 uses differential evolution, a population-based search method. Tier 4 adds transfer learning to adapt models across terminals. Tier 5 integrates everything in an operational digital twin for predictive system-wide decisions. Tier 1 treats Quay Crane assignment as a decision under uncertainty. Instead of optimizing for one assumed reality, it optimizes expected performance across multiple scenarios with different probabilities. This tier is the rigorous baseline. It defines the objects of the system, the decision variables, the objective, and a complete set of constraints. If a higher tier method is deployed, Tier 1 remains the reference for what correct and feasible means. This slide defines the core sets: the set of vessels, the set of quay cranes, and the set of scenarios that represent uncertainty. Operationally, the scenario set is how you encode real-world variability such as normal conditions versus equipment delays versus weather disruption. You are not guessing one future. You are planning across a small menu of plausible futures. Parameters describe the workload and productivity context. Vessel workload is measured in container moves. Productivity rates can vary by vessel, crane, and scenario. Each scenario has a probability. You also have operational limits. Each vessel has a minimum and maximum number of cranes it is allowed or required to receive, and there are interference factors that reduce productivity when cranes crowd each other. The main decision is binary, whether crane C is assigned to vessel V. In practice, this is the assignment map the operations manager issues. The model also includes a completion time variable for each vessel under each scenario. That variable turns assignments into a measurable service time outcome. The objective is to minimize expected total completion time across scenarios. In plain language, you minimize the probability-weighted sum of how long each vessel takes to finish. This objective aligns with terminal priorities. Faster completion reduces berth occupancy time, reduces delay risk, and improves overall throughput. The feasibility rule set has 4 pillars. First, each vessel must receive at least its minimum number of cranes and at most its maximum. Second, each crane can be assigned to at most one vessel. Third, completion time must be computed from workload divided by effective productivity under each scenario, including interference effects. The constraints together ensure that the solution is operationally executable, not a theoretical allocation. Minimum and maximum constraints represent contractual and physical limits. A large vessel may require at least a certain number of cranes to meet service-level commitments, while the maximum limits prevent unsafe crowding or infeasible work patterns. These constraints prevent 2 failure modes: starving a vessel below contractual service and over-allocating cranes to a single vessel where additional cranes do not translate into proportional productivity. This constraint enforces that a crane cannot work 2 vessels at the same time. Each crane is assigned to at most one vessel. Operationally, this is the no double booking rule. It prevents the plan from hiding resource conflicts that would appear immediately on the key. Completion time is computed as workload divided by effective productivity. Effective productivity depends on which cranes are assigned, how fast they work in the scenario, and how interference reduces output when cranes crowd. The key operational insight is diminishing returns. Adding a crane increases capacity, but interference can reduce the benefit. The model forces you to account for that trade-off explicitly. This visualization summarizes the Tier 1 model structure, showing how vessels, cranes, and scenario effects connect. Use it to connect the math to reality. Assignments are the levers, productivity and interference are the physics, and completion times are the outcomes. This example uses 3 vessels, 4 cranes, and 2 scenarios. The scenario probabilities are 0.7 and 0.3. The reported expected completion times are 16.5 hours for the first vessel and 25.8 hours for the second, yielding a total expected completion time of 42.3 hours. The example reports a 15% improvement over deterministic approaches that ignore uncertainty. Tier 2 uses beam search to produce high-quality assignments quickly. Instead of exploring every possibility, beam search keeps only the top K partial solutions at each step, based on a heuristic evaluation. This structure gives you a controllable trade-off. With a small beam width, you get speed, and with a larger beam width, you get higher solution quality, while still staying far below exhaustive search. This slide summarizes the time complexity behavior of beam search. In spoken terms, runtime grows with branching factor and depth, multiplied by the beam width. Operationally, the message is that compute time is tunable. You can adjust beam width based on how quickly you need an answer and how complex the live situation is. The algorithm structure diagram shows the beam search loop. Expand candidate assignments, score them, keep the top K, then proceed to the next decision level. This is operationally appealing because it is explainable. You can inspect which candidate assignments survived pruning and why, which builds trust with supervisors and planners. In the example, the instance has 4 vessels and 6 cranes, and the beam width is 3. The first level generates 15 combinations and keeps the top 3. The reported outcome is a total processing time of 23.4 hours, achieving 97% of optimal solution quality, while reducing computation time by 85% compared to an exact branch and bound method. This slide explains what you should look at in a beam search trace. At each level, candidates are expanded and then pruned down to the top K by a heuristic score. Operationally, pay attention to which partial assignments survive pruning, how interference and crane scarcity change rankings, and where feasibility constraints eliminate candidates early. Those are the decision points that explain the final assignment. This code section defines the beam search state representation and the heuristic used to score partial assignments. As you read, map the score back to operations. A good heuristic captures expected completion time, crane utilization, and interference penalties in a way that makes promising partial solutions rise to the top. This section expands candidate states and applies pruning to keep only the best K candidates at each level. The pruning step is what makes beam search practical. It prevents the search tree from exploding while still exploring more than a single greedy path. Tier 3 uses differential evolution, a population-based meta-heuristic that searches a continuous representation and then decodes into discrete Crane assignments. The advantage is exploration. Differential evolution can escape local optima that trap greedy and narrowly pruned searches, and it can improve global trade-offs like total completion time and Crane utilization balance. This slide shows the update pattern in differential evolution. You create a trial candidate by combining existing population members using a difference vector and a scaling factor, then apply crossover. Operationally, think of this as structured variation. The algorithm generates new assignment tendencies that are not random noise, but directional moves guided by differences between good solutions. This figure illustrates mutation, crossover, and selection as the three main operations driving improvement. The selection step is key. After generating trial candidates, only those that improve the objective or fitness are retained, which steadily pushes the population toward better allocations. The example uses 5 vessels and 8 cranes. The reported best fitness values over generations decrease from 187.3 hours at generation 1 to 126.8 hours by generation 1000. The example reports a 12% improvement over greedy heuristics and an average crane utilization of 84%. The takeaway is that population search can produce better global allocations when simple heuristics plateau. This code part defines the population initialization and the encoding of candidate solutions. Focus on how the continuous encoding is mapped back into feasible discrete assignments. That decoding step is where feasibility rules like min and max cranes per vessel are enforced. This section defines mutation and crossover to generate trial candidates. Good parameter choices matter. The scaling factor and crossover rate control how aggressively the search explores versus how conservatively it refines. This part evaluates trial candidates using a fitness function that reflects completion time and constraint feasibility. Operationally, fitness must penalize infeasible allocations strongly enough that the search does not drift toward unrealistic solutions. This final section performs selection and updates the population across generations. The output includes the best allocation found and its performance metrics, which allows you to compare against beam search and the baseline model. Tier 4 introduces transfer learning to reduce the cost of building predictive models for new terminals. Instead of training from scratch every time, you start from a pre-trained model, learned from other terminals, and adapt it to a new layout and operating pattern. The benefit is speed and generalization. If the model has learned reusable structure, it can adapt to a new terminal with much less data and much less time. The architecture includes a feature encoder that learns vessel and terminal features, an assignment predictor that outputs crane allocations, a domain adaptation component that reduces mismatch between terminals, and a constraint enforcement layer that projects predictions back into feasibility. Operationally, that last piece is critical. Prediction is only useful if the final output respects hard limits like min and max cranes and non-overlapping crane usage. The example describes training across 3 major ports, Rotterdam, Hamburg, and Shanghai, with more than 10,000 historical instances. The target is a new automated terminal in Long Beach with 6 berths and 15 cranes. The reported comparison is 95% accuracy after 120 hours when training from scratch, versus 98% accuracy after 80 hours using transfer learning, which is a 33% time reduction. It also reports an 18% processing time improvement. In a 7-day test, average turnaround improves from 19.7 hours to 16.2 hours. Crane utilization improves from 76% to 89%, and adaptation time is 2.3 hours. This code section defines the dataset interface and how a pre-trained model is loaded and prepared for fine-tuning. From an operations standpoint, this is where you ensure data fields are consistent across terminals, and where you prevent label leakage that could inflate reported accuracy. This section defines the domain adaptation logic and the training loop for fine-tuning. Operationally, the goal is to improve performance on the new terminal without forgetting the general patterns learned earlier. This part implements evaluation and accuracy tracking. Accuracy should be measured alongside constraint feasibility and operational KPIs, because a prediction that violates Crane limits is unusable even if it looks accurate on paper. This final section outputs the adapted model and demonstrates inference on new instances. In real deployment, you would also log confidence and monitor drift so the model does not degrade as operations change. Tier 5 uses a digital twin to integrate Quay Crane Assignment into a full system view. The digital twin continuously simulates the terminal, linking vessels, cranes, weather, maintenance, and operator behavior. This changes the decision style from reactive to proactive. You can predict bottlenecks before they happen and adjust crane assignments in near real time. The architecture includes real-time monitoring of crane health and performance, process models for vessel handling workflows, performance models for key performance indicators, and automated decision modules with human override. Operationally, this is not just automation. It is a coordinated decision system that learns from data and simulates consequences before pushing recommendations. The example describes a deployment at Los Angeles Terminal Island with 18 ship-to-shore cranes and 12 berth positions. It reports predictive accuracy of 94% for a 4-hour horizon and 87% for an 8-hour horizon. It reports operational improvements. Turnaround decreases from 22.3 hours to 18.7 hours. Crane utilization increases from 72% to 84%. And weather-related delays drop from 8.3% to 3.1%, described as a 62% reduction. Operational responsiveness includes updates every 30 seconds, scenario evaluation of 1.2 seconds for 10 scenarios, and operator notification latency of 0.8 seconds. It also reports a 23% overall efficiency improvement and a 40% human workload reduction. This code part defines the simulation environment and the event loop that drives time progression. The correctness of the digital twin depends on event ordering and state updates. If the simulation clock and state transitions are wrong, predictions and recommendations will be misleading. This section models crane dynamics, such as performance degradation, maintenance events, and assignment updates. Operationally, this is where you capture the reality that cranes are physical assets with health and variability, not static machines. This part integrates weather signals and their impact on productivity. The point is to anticipate disruption. If weather reduces effective rate, the system should reallocate cranes before queues and delays explode. This section adds decision logic and scenario evaluation, running multiple what-if futures. Operationally, this is how the digital twin supports proactive decisions. You are not waiting for failure. You are evaluating options before the failure happens. This part outputs KPIs and bottleneck indicators from simulation. These outputs are what operators and supervisors need: predicted turnaround, utilization, delay risk, and recommended actions. This final section includes notification logic and human override hooks. In real terminals, human override is essential. The system must remain auditable and safe, and recommendations must be explainable. The practice questions focus on implementation readiness. You practice building a stochastic model with scenario probabilities and interference effects, then implementing beam search with a chosen beam width. You also practice differential evolution encoding and decoding for feasible assignments, designing a domain adaptation approach for transfer learning, and designing a digital twin data flow with response rules for disruption scenarios. Quay Crane Assignment is a high-impact decision under uncertainty. Tier 1 provides the rigorous baseline model. Tier 2 provides fast, near-optimal decisions, and Tier 3 improves global trade-offs through population search. Tier 4 accelerates learning across terminals through transfer learning, and Tier 5 enables predictive, system-wide optimization through a digital twin approach.